All right, welcome back. We are going to be looking at section 7.3 today. But before we get started on today's notes, I would like you to flip back in your notes packet to our first page of notes. Let me find it here. I want you to get in the habit of highlighting key information. So on that first page of notes, you should have two rules. One is the zero exponent rule. The other was what we do with negative exponents. I want you to highlight those or circle them or put a big star by them. Do something that's going to make them jump out of the page at you. All right, because as we go through this chapter, we are going to be looking at a lot of different exponent rules, and it will be easier if you start going through and reviewing those as we go. All right, section 7.3 deals with multiplying powers that have the same base. So we're going to look at what kind of exponents do we have, exponent rules do we have for that when we have like bases. To get started, we are going to look at a couple examples. We have x squared times x to the third. If we were to write that out, x squared means we are taking x times x, and x cubed means we're taking x times x times x. But then it's telling me to times those pieces together. So how many total x's do we have? We had 2 here, we had 3 here. That means we have 5 x's being multiplied together. We can simplify that as x to the 5th. Similar example, this time our base is a 5. We have 5 to the 4th power, and we have the same base 5 to the 5th power. If we were to write that out the long way, the first one says we have 4 5s that are being multiplied together. Then we have 5 more of them. So in total, we have 9 5s being multiplied together. Now we'd like to come up with a rule so we don't have to write it out every time. And that rule states a to the mth power times a to the nth power. We can keep the base a, all right, as long as they match, we can keep it. And we can simply add the exponents together. All right, it is important that those bases are the same. So in this example, we have 2 squared times 3 squared. We have 2 different bases. They don't match. We can still do the problem. We could take 2 squared and say that's 4, and 3 squared is 9, and multiply it that way. But there are no shortcut or exponent rules that we can follow to do that type of question. All right, so in your packet, it asks you to state the rule both algebraically in words and to write down an example. Well, the algebraic method is what I had in the yellow box above. We can keep the base and simply add the 2 exponents together. All right, in words, I would say, well, let's go back. Let's actually put keep the base and add the exponents. All right, so an example, let's put down x to the 5th times x to the 7th. That shortcut, instead of writing all those x's out, says I can simply add my 2 powers together because I have a common base of x. So my answer would be x to the 12th. Some common errors to avoid. Do not multiply the bases. All right, we have 4 squared times 4 to the 3rd. That is simply 4 to the 5th. All right, we add those exponents, but we keep the same base. All right, it does not become 16. Okay, we'll do this. The second common thing, don't leave a negative exponent in your answer. We learned yesterday or a couple days ago how to deal with negative exponents. In this case, we have an x to the negative 3. That 2 does not have a negative exponent on it. It's just going to stay where it was. But the x, because it has a negative 3 exponent, is going to shift to the denominator to make our exponent positive. Our third common mistake is do not add the coefficients. We get in the habit of adding the exponents and we think, oh, we just keep adding the coefficients. Now remember, coefficients is that front number. Okay, so in this case, we can take this x and put them together. But the 3 and the 2, there is no shortcut. We have to just do what it says. All right, so we're going to take 2 times 3, and then we're going to take x times x to the negative fourth. All right, so 2 times 3 will give us a 6. X times x to the negative fourth. Notice that there is a power of 1 here that is not written, all right, but it is assumed. So if you see an x, it means you have x to the first power. So now if we add the exponents, 1 plus negative 4 would be negative 3. And then we go back to our previous common mistake. We don't want to leave it that way. We need to move that x to the third down into the denominator. All right. Let's look at some examples. We've got m to the third times m to the fourth. We want to write this using each base only once. That means any common bases we want to be able to put together. So we want to write this as just m to some power. And our shortcut says as long as our bases are the same, we can add our exponents. So we would have m to the seventh. Our next example has a common base of t. So we're going to have t as the base in our answer. Again, notice that there is an assumed exponent of 1 right there. And negative 5 plus 1 is negative 4. But we can't leave negative exponents, so we are going to have to flip that over, take its reciprocal, and get 1 over t to the fourth. And our third example, in this case, our common base is a negative 2. So we're going to have negative 2 to some power. And if we add these up, we have a 1 here, plus 3 more here is 4, and a negative 7 added to that gives us negative 3. So again, a negative exponent, we are going to have to flip that over. Okay, now something small like this, we could go ahead and simplify that. Negative 2 times negative 2 times negative 2 would be negative 8. All right. Go ahead and pause the video. I would like you to try to do, let's have you do the first 4. All right, go ahead and pause the video and try the first 4. All right, let's check our answers. We have a common base of z. Adding our exponents, 8 plus 5 should give us 13. In our next example, we have some coefficients. We have a negative 4 and we have a 6, those big numbers in front of our variables. We do not have any shortcuts for those, so we are going to have to multiply them. Negative 4 times 6 is negative 24. What we do have is we have common bases here and here. So k to the negative 3 and k to the 4. We can put that together as k to the first power. Now you don't have to put the 1 in there. You certainly can. It wouldn't be marked wrong, but it is equivalent to saying this. All right, our next one. Again, we have some coefficients. We are going to have to go ahead and multiply those together. 13 times 3 is 39. And then our x's. We do have that common base of x. We can add the exponents. Negative 8 plus 10 would be 2. And our fourth example, multiplying our negative 2 and 4, we get negative 8. Combining our h's, 5 plus negative 3 should be 2. All right. Moving on, we start adding in some extra variables. In this case, we have 3 places. All have the same base, though. They are all t's. So we are going to just add our exponents. 3 plus 6 plus 9. So we end up with t to the 18th. Our next one, we have a negative in front of that f to the negative 8. You can think of that as a negative 1. So we have negative 1 times 4 will give us a negative 4. We have f to the negative 8 power times f to the 12th power. We can add those powers. Negative 8 plus 12 is 4. All right, in the next one, notice that some of them are m's and some of them are n's. We can put all the m's together and we can put all the n's together. Let's start with our m's. Here we have m to the first, we have m squared, and we have another m to the first. Combining those would give us m to the fourth. When we look at our n's, the first one is an n squared. Then we have an n to the negative 4 and an n to the negative 1. All right, so combining our n's, we have 2 plus negative 4, that would be negative 2, plus the negative 1 would be negative 3. But again, we can never leave negative exponents. So in this case, the n term is going to have to move to the denominator. Our m to the fourth will stay where it was on the top, and our n will move to the bottom, n to the third. All right, go ahead and pause the video, and I want you to try the next 3. All right, checking our answers. We have a 6 times negative 4, so negative 24. We have an a cubed and an a here. We would have an a to the fourth. And then we have a b to the negative 2 and a b to the negative 8, so b to the negative 10. Hopefully you did not leave that as your final answer. It should simplify to be negative 24 a to the fourth divided by b to the 10th. That b term needs to move to the denominator. All right, next we have q to the fourth and q to the third. We get q to the 7th. Our r's, be careful here. We have r to the negative 5 and r to the positive 5. That's r to the 0 if we add those exponents. But remember, anything to the 0 is 1. All right, anything to the 0 is 1, and timesing by 1 does not change our answer. So we are going to just have q to the 7th. All right, next, our coefficients, negative 3 and 5, should be multiplied to be negative 15. Our c terms, we have a 7 and a negative 3. Adding those, we end up with c to the fourth. Our d term, we have a negative 2 and a positive 1. That is d to the negative 1. And again, because of that negative exponent, our d term will have to move to the denominator. You can put a little 1 exponent in there if you want, but it is not required. Notice that the negative 15 did not move down. It is not a negative exponent. Those are the only things that move. All right. Using those same rules, we are going to look at a couple things that are written in scientific notation and see if we can think of them in terms of the common bases again. All right. So we have coefficients here, or front numbers of 5 and 1. We can go ahead and multiply those together. All right, 5 times 1 is 5. And then we have a 10 to the 4th and a 10 to the 7th. Those are common bases. All right, both have 10s, which means we can add those pieces together and say that is 10 to the 11th. So what would we get on this next one? We have 7 times 10 to the 4th and 7 times 10 to the negative 5th. We can go ahead and multiply those two and get our 49. And then how many 10s do we have left? Well, we've got 4 here and negative 5 here. That's negative 1. Is that in scientific notation? Kind of looks like it, except our front number's too big. All right, 49 is too big. We need that to be 4.9. We can only have one number in front of our decimal. So let's think about what kind of exponent we need now on our 10. Right now our decimal is here, and this is saying we need to move one place to the left. So we would move to here. Well, that's what we have down here. So we don't need any more moves to get us back to where we need to be. Now, 10 to the 0 is 1, following our 0 rule. So we could just write this as 4.9. It is equivalent. All right. It says the population of a country in 1950 was 6.2 times 10 to the 7th. The population in 2030 is projected to be 3 times 10 to the 2nd times the original population. So we are going to have to take 6.2 times 10 to the 7th and multiply it I'll use parentheses instead of another multiplication symbol, times 3 times 10 squared. All right, doing the same thing we just did. We've just included a word problem example of it. We want to take 6.2 times 3. That gives us 18.6. And then we want to combine our tens. We have 7 in the first and 2 in the second, so that's 10 to the ninth. But again, we aren't in scientific notation, in proper scientific notation. Our decimal point needs to move to there. So we want this as 1.86. And how many spaces do we have to go? Well, originally we were going to move 9 spaces to the right, so we would go 9 this way. If we back up and put our decimal here, that now means we have 1 more space we have to move to get back to where we were headed. So we are going to need an exponent of 10. All right, our last examples. It says to write an expression for the area of each figure. Now, hopefully you remember from middle school, area of a rectangle is length times width. So we have a length of this and we have a width of this. All right, we have to multiply those two together. So 4x squared needs to be multiplied to 3x squared plus 2x. But this is a case of having to distribute because we do have that addition sign here. We are going to have to multiply the 4x squared to that first term, and then again we have to multiply it to our second term. So in this case, 4 times 3 would be 12. X squared times x squared would be x to the fourth. Distributing to our second term, we have 4 times 2, and we have x squared times x. And that would be another way of saying the area of that rectangle. All right, our last one is a triangle. And the area of a triangle's formula is a little different. It's 1/2 base times height. All right, so we're going to have 1/2. Our base is 2b squared minus 4, and our height is 5b. All right, well, let's distribute that 1/2. What's 1/2 of 2b squared? Half of 2 is 1. So we have b squared. Half of 4 is 2. So we are minusing 2. And then that is getting distributed with that 5b. All right, 5b times b squared, multiplying those, gives us 5b to the third. We add our exponents. And remember, there's a 1 right there that we don't see. And then distributing here, we have negative 10b. All right, so our main rule for this unit, or this section, was this one. If you have a common base raised to 2 different powers, we can add those powers together. All right, so at the end of your notes for today, there should be a summary section. Go ahead and take a minute and fill in a couple sentences for your summary, and then your assignment is worksheet 7.3. And again, remember to show your work.